Hello, welcome to my presentation on distributed systems. Here I'm going to talk about a way of performing replicated data updates, just as view stamp replication that we previously read about. The method is named as situation-aware updates and crash recovery. And here I'm going to call it by its short SAUCR. To talk about the motivation of inventing this protocol and apply it in replicated data updates, we have to talk about three dreams that people always have about such system. The first dream is to achieve high performance, which basically means higher throughputs in a unit time duration. The second dream is to have strong durability, which means we want no loss in terms of data in our system. No matter what happens, that's the ideal one. The third dream is about strong availability, which means how the system gonna ensure its stability and continue to work and provide service to its clients. Usually those dreams cannot be realized at the same time because if we want high performance, here we will run the replication on memory because it is faster than disk durable protocol. However, if you want to maximize the durability and availability of the system, we will write every modification on disk since information on disk is assumed to have no loss. But at the same time, the performance will be very poor because it relies purely on disk. And here are those characteristics of those two protocols, which refer to store in memory and store in disk, becomes the biggest motivation of designing SAUCR. Because if we run fast on memory when there's no failure, and run safely on disk when there is a certain amount of failure, we are guaranteed to have a system that can approximately be reliable and fast. And first thing first, I'm going to talk about the system models that we have to establish before diving into the real algorithms of SAUCR. The first aspect is about the failure model and the basic assumptions that are that all the failures we talk about can only be failure, recover, failure, fail, recover failures, and there should be no Byzantine failure. There are three kinds of situation that may happen. The first one is an independent failure, which is not a big deal because as the paper said, the chance of a lot of independent failure happening at exactly the same time is usually rare. The second is the non-simultaneous correlated failure, which can have a good chance of failing the majority of the nodes and might become deadly for memory durable protocols, just as we previously mentioned. However, you will see this non-simultaneity give our SAUCR time to react and switch mode from fast to safe. Furthermore, the last kind is also very rare situation because based on their research from data provided by Google, the chance for all correlated failures to happen within a few milliseconds is very, very low. So let's just keep this in mind. By the way, the network is asynchronous and the message will eventually be delivered. Those are some basic assumptions. And we will use figure 3 to give an intuition about how SAUCR modes work. But firstly, here are 5 nodes, and there are some definitions that I need to introduce first. As we can see here, the the bare majority is this, and the bare minority is this. And for this distributed system, the bare minority is 2, and the bare majority is 3. At first, all the nodes are functional, and hence the leader S1 replicates entry E1 in fast mode. As you can see here, I circled. The follower acknowledges E1 before persisting it. Similarly, the leader also buffers E1 in memory. In fast mode, the leader acknowledges an update only after two E+1 nodes have buffered the update. Because there are at least 4 nodes have buffered E1. The leader acknowledges E1 as committed, and now it's going to tackling E2. Now S5 crashes. The leader detects this but remains in fast mode and commits E2 in fast mode in the same fashion. Next, S4 also crashes, as you can see here. So now we are leaving behind a bare majority because we have only 3 nodes that is not crashed. At this time, the leader will now immediately initiate a switch to slow mode. As you can see here, it is switched to slow mode. And now it will replicate all subsequent entries in slow mode within the latency of heartbeat. I mean, the reaction latency is shorter than the heartbeat. In this fashion, E3 is replicated in slow mode as you can see here, or actually here. Committing on an entry in slow mode requires at least a bare majority, which is 3 here, to persist the entry to their disk. Hence, when E3 is persisted on 3 nodes, it is committed. Further, the first entry persisted in slow mode also persists all previous entries buffered in memory, which are those entries. And now they will all be persisted in slow mode. And in that case, meanwhile, S4 and S5 recovered and catch up with other nodes, and once some condition is satisfied, the mode is switched back to fast mode. And at this time, E4 will be committed in fast mode until there is some further failures. Here we need to talk about the mechanism behind mode switch in SAUCR. Firstly, the command of the mode switch is made by the leader, as you can see here, the leader, who will listen to the heartbeat of other nodes, as you can see here. When in fast mode, the nodes periodically flush their buffer to the disk in the background without impacting the client perceived performance. However, if the leader here suspects only a bare majority of nodes are good, as you can see here, the leader can only hear from 2 other nodes. The leader will then send a special request to all its followers, which makes them switch to slow mode, as you can see here. However, if a leader failed at some time the leader failed, the followers will quickly detect that through heartbeat and flush all their buffer data to disk. Again, the background flush I mentioned previously will reduce the amount of data that needs to be written at this time. And at the same time, we need to talk more about the recovery when we do a hybrid fashion of memory durable and disk durable, because once a node recovers from the crash, it must know how many entries it had logged in memory and how many entries it had logged into disk before it crashed. Therefore, we refer this value as the last log entry, which is known as LLE. And the LLE recovery step is crucial because only if a node knows its LLE, it can participate in elections. If a node recovers from a slow crash, it can recover its LLE directly from the disk. However, if a node recovers from a fast mode crash, it would not have its LLE on disk. In this case, it has to recover its LLE from other nodes, which will be mentioned later. Okay, at the foundation of all those intuitions, let us take a detailed look at how modes in SAUCR change during the different amount of non-simultaneous failures. Okay, first, here, as you can see, if the count of failures is less than a bare minority, the system will be both available and fast. But on this occasion, if the nodes want to recover, we have to mention LLE again. A SAUCR mode recovering from fast mode crash recovers its LLE by first mark itself to be in a state called recovering. So the node will be in recovering state, and then they will send an LLE query to all other nodes, and therefore recover their LLE from other nodes. Okay, if a leader detects that we have a bare minority amount of nodes failed, the mode will be switched to available slow here, as you can see. Um, and if nodes more than the majority come back longer than a certain amount of time, the fast mode switch condition will be met. That basically means they come back for some time that we preset, and here the time have to be longer than a certain amount because we want to prevent side effects caused by fluctuation. And now if it is in available slow mode and which is here, and it will go to temporary unavailable mode if any node fail. Since it's already in this durable mode, it will recover until functional nodes are bigger or equal than the bare majority. Simultaneous failures of bare majority node will straight up trigger the temporarily unavailable mode because it is proved in paper that the system and LLE will be able to come back in this mode. You can refer more to the 3.5 part in this paper. However, based on assumptions that this happens in a very low probability, so I'm going to skip it right now. And also, the simultaneous crash of more than bare majority will lead the system to permanent unavailable, which is disastrous, but it basically does not happen from the perspective of probability. After learning the mechanism of the system, I'm going to talk about the strengths of SAUCR. The system is implemented and tested in this paper on Zookeeper, and we can see SAUCR will have exactly the same characteristics as the paper portrayed. And also, as we can see on the right side here, the SAUCR only has a 0% to 9% deduction on benchmarks compared with memory durable system in terms of performance. So it is quite strong and balanced in achieving the availability and durability while maintaining a decent performance. Here I'm going to talk about the weakness of SAUCR. The first weakness is over its sheer complexity that cause the protocol way harder to implement compared with other protocols. Because the contents, the information about LLE that we talked about before, is also an extra task for implementation compared with other protocols. Therefore, it's indeed harder to implement. Also, it will require hard drive and is slower than memory durable, which is also discussed in the paper. And therefore, thanks for listening to my presentation. And here's my reference, which is the paper of SAUCR.